The sun over the Dasht-e Lut desert does not merely heat, it sterilizes. Surface temperatures on the Iranian plateau regularly breach 60 degrees Celsius, a thermal assault that renders the landscape into a kiln of baked earth and silence. Survival here is not a matter of endurance but of thermal management. In this geography of extremes, where water evaporates before it hits the ground and the horizon shimmers with heat haze, a singular architectural anomaly rises from the dust. It is a conical dome, stepped like a ziggurat, built of mud and isolation. This is the Yak-Chow. It is not a dwelling. It is a machine. Designed to millennia before the compressor, it harvested the cold of deep space to create ice in the middle of a blazing summer. The physical reality of the Yak-Chow challenges the modern understanding of thermodynamics. It operates on a cycle of radiative cooling and thermal inertia that requires no electricity, no chemical refrigerants, and no moving parts. The structure dominates the skyline of cities like Yazd and Kerman, rising 18 meters from the desert floor. Its silhouette is deceptive. The visible dome is merely the exhaust port of a massive subterranean engine designed to manipulate air density on radiation. The engineering required to freeze water in a climate that rarely drops below freezing relies on a precise manipulation of the electromagnetic spectrum. The desert sky, stripped of water vapor, opens a window to the cosmos. At night, the ground radiates heat in the long-wave infrared spectrum, specifically between 7 and 14 microns, directly into the void of space. Space acts as an infinite heat sink with a temperature of near absolute zero. Under clear, dry conditions, a surface facing this void will shed energy faster than the ambient air can replenish it. The result is a temperature depression where water in a shallow pool can freeze even when the air temperature hovers at a positive 10 degrees Celsius. The logistical operation of the Yak-Chow begins not with the dome, but with the wall. To the north of the structure lies the shadow. A massive adobe wall, constructed with an east-west orientation, stretches up to 10 meters high and 12 meters long. This is the shading wall. Its purpose is to surgically remove the sun from the equation. At the base of this wall, on the northern side, lie the freezing pools. These are shallow trenches, roughly 400 square meters in area but only 40 centimeters deep. The water is fed into these pools from the Qanats, the ancient underground aqueducts that bring snowmelt from the distant mountains, keeping the water pre-cooled by the Earth's constant subterranean temperature. The process of ice creation is a war of attrition against heat. It occurs only in the dead of winter nights. Villagers would channel a thin layer of water into the shadowed pools. As the heat radiates into the night sky, a thin crust of ice forms. The workers do not harvest it immediately. They disturb it. They break the crust to ensure the water underneath freezes, or they add another thin layer of water atop the first. This continues for 8 consecutive nights. Layer upon layer of ice is built up, creating a monolithic block half a meter thick. The labor is brutal and nocturnal. The air is cold, but the work generates heat. The silence of the desert is broken by the sound of picks and the slosh of freezing water. Once the ice reaches the requisite thickness, it is cut into blocks and dragged into the repository. The repository is the heart of the machine. The Yak-Chow dome covers a deep pit, often excavated 10 to 15 meters into the earth. The volume of this storage space can exceed 5,000 cubic meters. The physics of the pit utilizes the stable temperature of the Earth's crust. Below 6 meters of depth, the soil temperature stabilizes, insulated from the diurnal swings of the surface. But the Earth alone is not enough to keep ice through a July heat wave. The structure itself must be an insulator of absolute efficiency. This necessity gave rise to Sarooj, a mortar of immense technical complexity. The creation of Sarooj is not masonry, it is chemistry. The mixture consists of specific ratios of clay, sand, lime, and ash. To this mineral base, the builders added organic polymers, goat hair, egg whites, and sometimes fats or lemon juice. The ash acts as a pozzolan, reacting with the lime and water to form calcium silicate hydrates, the binding agent found in modern cement, but with a slower, more deliberate curing process. The goat hair provides tensile reinforcement, preventing the mortar from cracking under the thermal stress of the desert day and night cycles. The egg whites and fats serve as hydrophobic agents, rendering the mortar waterproof. The preparation of Sarooj was a visceral, foul-smelling industrial process. The clay and lime were mixed with water and kneaded for days. The mixture was often fermented to ensure the complete hydration of the lime. Workers would tread the mud, mixing in the animal hair and ash until the consistency was plastic and uniform. In some traditions, the clay was first molded into blocks called Dasht-e-Lut, dried in the sun, and then burned in a kiln fueled by animal dung to activate the silica and alumina within the soil before being pulverized back into powder for the final mix. The resulting mortar was plastered over the adobe bricks of the Yak-H-Chal walls. These walls are massive, often 2 meters thick at the base. The thermal lag of a wall this thick is profound. Heat striking the exterior of the dome takes approximately 365 days to travel through the masonry to the interior. The wall effectively stores the cold of the winter and releases it into the interior during the summer, while the heat of the summer only reaches the interior when the winter returns. The building does not just insulate, it operates on a different temporal frequency than the seasons outside. The shape of the dome is a masterclass in thermodynamic airflow. It is a stepped cone. The steps are not merely for structural stability, or to aid the workers who must climb the exterior to maintain the plaster. They increase the surface area for heat dissipation. At the very apex of the dome is a vent, often shielded from the sun but open to the wind. This is the exhaust. Inside the pit, as the heat slowly penetrates or enters through the access doors, the air warms slightly. Warm air becomes less dense and rises. The conical shape accelerates this rising column of air, funneling it toward the vent. As the warm air escapes the top, it creates a negative pressure zone at the bottom of the pit, drawing in cooler, denser air from the base or from adjoining windcatchers. These windcatchers, or badgers, are often integrated into the Yak-H-Chal complex. They are vertical towers with openings facing the prevailing winds. The wind is caught, forced down the shaft, and often passed over a pool of water or the damp earth of the Q-anode connection. The air undergoes evaporative cooling. As water transitions from liquid to vapor, it absorbs a significant amount of latent heat from the air. This chilled, humidified air is heavier than the dried desert and sinks into the storage pit, washing over the stored ice. The interplay of the windcatcher's downdraft and the dome's updraft creates a continuous, passive circulation engine that keeps the core of the Yak-H-Chal at freezing temperatures while the stones outside bake at 50 degrees. The storage of the ice was as methodical as its production. The blocks harvested from the pools were not thrown haphazardly into the pit. They were stacked with layers of insulation between them. Straw and brushwood were placed between the layers of ice to prevent them from fusing into a single, unmanageable monolith and to provide further thermal isolation. The bottom of the pit was equipped with a drainage system, a well or a channel connecting back to the Q-anode to carry away any meltwater. Standing water is the enemy of ice as high thermal conductivity would accelerate melting. The Persians ensured the ice remained dry. The ice preserved in these vaults served an empire. It was not merely a luxury for the court, it was a commodity accessible to the populace. In the blistering heat of Isfahan and Shiraz, Sherbatan def Aludeh Horst Apples. Aludeh, a precursor to modern frozen desserts, consisted of thin vermicelli noodles made from starch, suspended in a semi-frozen syrup of sugar and rose water. The sensation of consuming ice in the middle of a desert summer is a sensory shock, a defiance of the environment. The Yak-H-Chal made this defiance routine. Donkey caravans would transport great chunks of ice from the repositories to the bazaars, the panniers dripping in the heat, the core of the load remaining solid. This technology was not static. It traveled. The knowledge of ice storage and evaporative cooling moved along the Silk Road. The Mongol invasions, while destructive, acted as a vector for technological transmission. The specific terminology of the Yak-H Chowspiyat is Persian, but the practice of managing cold spread into the Mughal courts of India. There, the technology adapted. The Mughals, lacking the extreme radiative cooling conditions of the high Iranian plateau in some regions, relied on transporting ice from the Himalayas and storing it in massive pits, using the same principles of thermal mass and insulation refined in Persia. The Mughal Emperor, Akbar, established a relay system, not unlike the Yam Postal Service, but for ice, moving it via boats and carriages to the capital, insulated with felt and straw. The chemistry of cooling evolved as well. The use of salpteed to lower the freezing point of water was recorded in Mughal annals, a chemical adjunct to the physical engineering of the pit. The biology of the region adapted to this landscape of heat and scarcity, alongside the architecture. While the Yak-H Chow managed thermal stress through static mass, the animals of the steppe and desert managed it through physiology. The Mongol horse, the engine of the empires that swept across these lands, possessed a metabolism tuned for survival on marginal intake. These animals, much like the camels that carried the ice, were biological machines of efficiency. While the sources provided do not detail their specific blood chemistry, the context of the region dictates a reliance on animals that could endure the same dehydration and thermal load that the Yak-H Chow was built to negate. The decline of the Yak-H Chow was not due to a failure of engineering, but a shift in energy economics. The introduction of the electric refrigerator and the industrial ice plant rendered the passive harvesting of ice obsolete. The labor-intensive process of nighttime harvesting and the annual maintenance of the adobe walls could not compete with the flip of a switch. The Sarooj Krat. The domes, once covered in thatch to shield them from the summer sun, were left bare to erode under the wind and drain. Of the hundreds that once dotted the landscape, only a fraction remained standing, their mud brick skeletons dissolving back into the geology from which they were raised. Yet, the obsolescence is technical, not functional. The physics remain absolute. Modern analysis of the Yak-H Chow reveals a thermal performance that rivals contemporary sustainable design. The heat transfer coefficient of the walls, the efficiency of the Windcatchers, and the exploitation of night sky radiation are being re-examined by engineers seeking to decouple cooling from the electrical grid. The Yak-H Chow stands as proof that the conquest of heat does not require the brute force of compression cycles and refrigerants. It requires only an understanding of the sky, the earth, and the geometry of shadow. The silence inside a Yak-H Chow is heavy, insulated from the acoustic and thermal chaos of the outside world. It is a cold, dark testament to a civilization that looked at a freezing void and saw a resource.